Okay, good morning and welcome to the last day of our summer school. And it's my pleasure to give the floor to Jasmin Raissy for her last lecture about dynamics.
Thank you very much. Well, thank you all for coming. I know it's hard to come at 9:30, especially after the nice dinner that we had yesterday. It was very nice. I hope you enjoyed it, like I did. So, well, but now we're back to work, back to dynamics. So I wrote on the board, so yesterday, actually this morning I woke up earlier to remind myself what I really needed in the result, what were the hypotheses that I needed. So we're going to talk a little of parabolic dynamics in dimension 1, and actually, so you don't need to have degree 4 in the result that we have, but we need to have degree 3. So there is this A here, which is going to play a role. And yes, you notice that I also prepared a little work so to be able to be a little faster. But I didn't bring slides because I think the whiteboard is nicer. So this A here is going to play a role. So there is one thing that I would like to stress out. So today I'm going to give you ideas in the proof of a well-known result, which is called the Fatou flower theorem. So it's just going to be very sketchy. And in the Fatou flower theorem, you don't need to say anything about this part. All you need to know is to consider the first nonlinear term. But since I will need it, I mean, you know, when you construct you're teaching, when you construct a course, you always have to have a balance in between what you need to prove the theorem you want to prove and the most general case. Okay, so the most general case of the Fatou flower theorem, you find it in any possible book of complex dynamics in dimension 1. So let me write here on the board the name of and this is related to local dynamics. So the local dynamics, so this is a remark if you want, and this is not the right pen. So the local, this is not the right pen also. Let me see. This is like better. The local dynamics of, well, a function defined from a neighborhood of the origin. So the origin belongs to this neighborhood towards the same neighborhood of the origin. So holomorphic function fixing the origin and such that the derivative at 0 is 1. So it's starting like the identity, but f is different from the identity, is described by the Fatou flower theorem. So if you want to know what happens, it's really, so locally, so you fix yourself, you give yourself a neighborhood of the origin, and you say you want to know what happens in this neighborhood of the origin. What happens means, if I give you a point in here, where is it going to go its orbit? This is what I mean by what happens. This will be told by the Fatou flower theorem. So in our case, we're going to see an instance of this result in this very particular case where the first nonlinear term is of degree 2. Okay? And this 2 here is pretty important. So in order to understand, is easier if we do it like this. So as an example, if I have phi of z, let me write phi because then it's different from f. Phi of z, which is of the form z plus z squared, and nothing more. Actually, let me also do it a little easier. Let me put a minus in here, just for the sake of simplicity, so that we don't have to twist on our minds. Well, you see that you can write this like z times 1 minus z. Okay, and that's, I know that it's completely stupid as an observation, but that's the observation. Because now, this is c. So this is the real line, and this is the imaginary axis. Okay? So now if I am at the origin, well, the origin is fixed. Okay? What happens if I take the point 1 over 2? f of 1 over 2, well, let's see what happens. It's 1 over 2 times 1 minus 1 over 2. So it's 1 over 4, which is less than 1 over 2, right? I mean, that's, you agree with me? Like, just, this is standard, not even first year of undergrad math, right? But now what happens if x is real and say, well, less than 1? Then f of x is, sorry, phi. That's a, sorry, phi. Phi of x is going to be x times 1 minus x. This is real. This is still real. And so it's going to be less than x. Okay, because it's x minus x squared, and x squared is a positive real number. So what's going to happen is that if 1 is here, for every point in here, well, the iterate is going to go like this, and like this, and like this. And so, well, let's take this out. You're going to converge punctually on the real axis to the origin. So what happens if I actually, in here, I wanted something which is real and positive? What happens if x, is real but negative? Well, if x is real but negative, then this is going to be bigger than 1, because 1 minus x, 1 minus 1 over 2 is going to be equal to 3 over 2, right? And so what's happening is that I'm going to go out or far away from the origin. And since I have a polynomial, I can do this for every point on the line. Okay? There is 1 in here, which is a problem, so we will not touch it for the moment. But in here, I'm going to go towards infinity on this side. And so, but this doesn't give you any idea on what happens in a full neighborhood of the origin, right? And so, well, what the theorem for the Fatou flower theorem tells you is that you're going to have, well, first of all, it tells you that you're going to have some sort of sectors that I'm going to do in different colors, where in here the dynamics goes out infinitely many steps, and in here, well, the dynamics goes towards the origin with actually with a very well precise behavior. So you're going to go to converge to the origin being tangent to this axis of the sector. But again, you agree with me that this is not yet a full neighborhood of the origin. And what the Fatou flower theorem tells you is that indeed you can find, sorry, I'm going to take out 1 in here. I'm going to put it here. So you have a bigger open domain where this happens. So in here, the orbits are going exactly to do what I'm saying in here, what I'm drawing. And you're going to have a symmetric open set where actually, so if I'm considering a polynomial, I can say I go out of this open set, the red open set, infinitely many steps. But if you are considering a local map, it might be that to go out of it, to go out of this, I mean, you cannot iterate anymore when you go out of U. And so it makes more sense to talk about the inverse of F. So this red petal is going to be abstracting for the inverse of F. Okay? And so this is more or less what the Fatou theorem tells you. Okay? And this is not a proof. So this is just a motivation or some ideas in the proof. How do one prove this kind of theorem? Well, the problem is that, well, it's already difficult to iterate this map, right? Because at each time you have to multiply z times 1 minus z times 1 minus z1 times 1 minus z2, and so on and so forth, right? And so it's a lot of products. So what's easier for us? It's easier, as we were saying yesterday, to use sums. I mean, sums are better understood or easier to understood than products. Okay? And so the idea is, sorry, I'm not going to use this anymore, not for the moment. So the idea is to consider the variable u equals to minus 1 over z for f. Okay, so in here, I'm going to stick to this case where I put a plus in here, so I need to have it with a plus, because you remember the skew product we have, there is a z plus z squared plus something, w minus w squared. And this is really important. I mean, this is something that we really need. We can work it out also if you have both plus and both minus, but that's more difficult. All right? And so, well, I left you an exercise. So in the u coordinate, little f becomes capital F of, maybe capital is not a good idea. Well, yeah, let me write capital F, I'm sorry, of u equals to u plus 1 plus b over u plus a big O of 1 over u squared, where b is equal to 1 minus a. In particular, what happens when R is big enough for R real big enough and, U in C such that the real part of U is bigger than R? So what happens when I put myself in, so this is the U plane. Well, if I start far away from the origin, well, if I take a point in here, so this is my initial point u0, so what's its image? Its image, well, I had to add 1, so this is u0 plus 1, and then, well, b over u is going to be super tiny with respect to this translation. And 1 over u squared is going to be super tiny as well. All right? And so actually, what my image is going to be, it is going to land in a very small disk around u0 plus 1. So this is where the image, so up, using capital F, is going. And so, well, you see that I'm going to stay in this domain. Then the real part of f of u is going to still be bigger. Actually, it's going to be bigger than the real part of u. This is important. Bigger. Well, actually, let me write it like this, because it's easier. So if you can find R big enough such that this is bigger than the real part of u plus 1 over 2, which is bigger of R. And why do I need this? Because now, if you iterate again, you're going to get an n in here. Okay? And so this tells you that, capital F of this real part of u bigger than R is strictly contained in this right half plane. And on this setting, so I'm going to give it a name, capital HR. On HR, the iterate fk of n converge. Well, actually, converge is not a good thing to say. So, diverge locally, uniformly to infinity. And on top of it, we can also say how they go. I mean, there is also velocity. You've seen un, uk, is going to be equal to u0 plus k plus a little o of 1 over uk minus 1. Okay? But, well, you can work this out. And so you can prove, so there is a proof in here. One can prove that uk is going to behave like k, as k tends to infinity. And why do I need this? Because this is very important for coming back. So not only I can say that I'm going to go towards 0 in the z parameter. So if I now take this, so this was a right half plane. Okay? So let's write it as a right half plane. So we're working in this part. Now we go back. Okay? We go back to our original z plane. So this was the z plane. All right? And so this is going to give us some sort of open set. This is not yet going to give us these petals. To get the petals, one has to have enlarged this somehow like this, because otherwise you cannot get bigger petals. But at the beginning, so this is exactly how Lo and Fatou do this. So I don't suggest, I did it when I was more or less your age, maybe a little younger. I went and read the original papers of Lo and Fatou. These are not math like we write it today. So it's like a flow of words. There is never theorem, there is never definition, there is never proof written. It's written all in French, by the way, so you also need to know French. And it's really like they are telling you a story. So mathematics has evolved a lot. In particular, the paper of Fatou, it was really difficult to, but they also have all these pictures. I mean, it's interesting to also see sometimes how mathematics changed during the years. So that's how they prove that goes. And of course, if you are in such a region, then you will have to make sure that whenever you're near by the boundary, you're still really going to get something which is sent to itself. But that's another story. You find a wonderfully written proof of this result in Milner's book. I mean, that's where I would go to see it. And but if you don't like that one, I suggest checking some lecture notes of Marco Abate, and I think it's local dynamics. He has several versions of it, and there are all the computations. There are not that many pictures, but all the computations are done over there. Anyways, so we have this result, and so yes. So let me tell you then what we need here, which means, so this means that for r small enough, this is what's going to happen. And that's not difficult to prove. All right, so if r is positive, is small enough, sorry. Yes, f, Maya f, which was here, maps the disk. So this is the disk of center minus r and radius r into itself. All right? And so actually what we're going to have is the following. So remember, our f is of the form z plus z squared plus az cubed plus I other terms. Okay? So what's going to happen is that I'm going to have a minus r in here. So this is this is not a disk. This doesn't even look like a disk. Well, a little better. So this is my disk of center minus r and radius r. Okay, this is 0. And it's going to do the same with this other one. So this is going to be the attracting one. And you're going to have, similarly on this side, this disk of center r and radius r. Okay, so this is going to be repelling. So, and this is going to be attracting. And yes. And whenever you are, so this is something that you can prove. So for every z in, well, z naught in this disk of center minus r, so in this little petal in here, zk, which is by definition the kth iterate of z naught, is going to converge to the origin as k tends to infinity, and zk is going to behave like 1 over k. Okay? So this comes from this restriction that we did here. So if we had had z plus z cubed or z minus z cubed, then you would have needed to use 1 over z to the power 2, which means that you have a branch covering, and so you're still going to be able to prove the same result, but the velocity, so the rate of convergence is going to change. So it would have been 1 over square root of k. Okay? So this is why I'm doing it in this baby case. Well, because the computation are kind of a little easier. We don't have to take branches of the logarithm to take roots. Because of course it's always easy to take powers, but if you want to get back, you have to take a square root or a third root of of z, and so on and so forth. And so it's becoming more technical. All right. So are you okay? Are you still with me for the moment? So actually, yes, as an exercise, because I have to leave exercise. Well, fill in the details. This is a different exercise, of course. Fill in the details for this blah blah that I'm doing at the board. Okay, so now remember we are doing, so this is the local point of view, but we are doing global dynamics. And so now you trust me, we have something which is defined locally, and we can say, oh, we're going to consider all the points whose iterate land in this tiny little disk. And if you land in the disk, so if you're far away, if you land in the disk, then you're going to converge to the origin, right? Okay, so this is going to be the parabolic basin in here. Up. All right, I'm going to also erase here so that I can write my flow of things. All right. Good. So the parabolic basin of f at 0 is, I'm going to write it, which is going to be equal the open set of points whose orbit under iteration converges, well, actually, sorry, lands in, yes, intersect this disk that I fix. And this is going to be for all r greater than 0. So if you want, you can consider all the preimages of this disk for all the disks. So it's an intersection of all the union of all the preimages among R. So just because I cannot, sorry, I'm slower than I should be, but it's important that you know. So what one can prove is that, well, thanks to the Fatou flower theorem, since you can enlarge these two guys to make them intersect, in order to converge to the origin, you need to land in this guy. So that's something that it's somehow called a base for convergence. So in order to converge to the origin in this setting, in this tangent to the identity setting, you will have to land in one of these disks. Of course, if I'm taking the intersections, I might have, like this is minus R0, and this is smaller and smaller, but I have to land in one of those if I want to converge to the origin. Okay? You see what I mean? And so this is why we can define the parabolic basing like this. Of course, we could do it like since we have uniform convergence in one of these disks, I can take the maximal open set, connected open set, which contains it. That's a Fatou component. Okay? But that's the same. Whatever the definition, okay, so yes. So I'm going to give you a definition here, which is going to give us a model. So whenever we are in the attracting or in the repelling basin, the idea is that, well, we use some sort of approximation of a good coordinate where we were conjugating to almost the translation by one. And what the Fatou-Flower theorem tells you is that actually this is possible to, it is possible to conjugate on the petal to the translation by one. So it's not possible to conjugate all over C to the translation by one. This is not possible, except for a very, very particular case. But you can still do something inside these disks, inside the parabolic basin. And so, well, yes, let me write it like this. So this is a proposition, which is indeed also a definition. Okay, so there exists a, well, unique up to up to constants coordinate that I'm going to call capital phi of f, which is defined from the basin, and it's going to land in C, which is called an attracting Fatou coordinate. Which is holomorphic, of course. So let me write it here. So it's holomorphic on this basing, and it's semi-conjugating f to the translation by 1. T1 of u, which is equal to u plus 1. So we don't have that tail that we were having before. And the price to pay is that you have to build it. So actually, it's kind of a snail coming back. So first you prove by using an approximation of this coordinate that you can find this open set. Then you have the open set, and you work on the open set by proving that you can indeed conjugate to the translation by 1. And one way to do it is simple, easy, complex analysis in dimension 1. You build up, using the dynamics, a sequence of holomorphic maps which semi-conjugates it nearer and nearer to this translation by 1. Then you prove that it's Cauchy. Done. Then it converges. So life is easy. All right, we are not going to prove it. So semi-conjugating means that it might not be invertible all over the basing. Actually, it's not. But all over C, but it's going to do what we want it to. So this means that phi of f composed with f is going to be equal to, well, the translation composed with phi of f. So usually what we write is that phi of f of z is equal to phi of f of z plus 1. Okay? And well, actually, moreover, and such that, well, this is kind of very important for us, is we can write down its asymptotic development at infinity. So this is going to be equal to minus 1 over z, as we saw before, minus b log of minus 1 over z. I'm going to tell you which branch I'm taking, plus little o of 1 as the real part of minus 1 over z goes to infinity. Yes, plus infinity. We're in the log, the branch of log. So this is the branch of log defined on c minus r minus and vanishing at 1. All right. Yes. Okay. And, well, actually, the fact that it is unique up to an additive constant, this is something that you can prove. So this is an exercise. Once you have this, it's easy to prove that if you have two, they have to differ by a constant. Okay? All right. So I'm not going to prove this, even if I had planned to. But, well, I still have 20 minutes. Well, 25 minutes. Because 25 minutes. I know that. So, actually, as I was saying, well, we are doing everything in the attracting part, but we could also see what happens for the inverse of f. All right? And so, well, this is called somehow the repelling basin. The repelling basin, so the repelling basin, let me write it down, is going to be equal to the attracting basin, so the parabolic basin, for f inverse. And now I'm being very sketchy because this is not completely correct. Because f inverse might not be defined everywhere. I mean, we had a polynomial, but the inverse of a polynomial is never a polynomial in dimension 1, except when you have an affine map. But our polynomial has degree at least 3. But, well, so let me put quotes in here, because if I'm in a small neighborhood, everything is local. If I'm in a small neighborhood, I will be able to do this. Okay? So I will do this wherever I can do it. And then I need it really, because otherwise I cannot work on this, guys. So we need the so-called the Fatou parametrization. On the repelling petal, what's going to happen is that you are going to have a repelling Fatou coordinate, which is going to be an attracting Fatou coordinate for the inverse. So I will have f inverse here. Well, this is not quite well defined. What is well defined is the parametrization, so it's inverse. And this is what I'm going to state. So the proposition that we have is the following. Again, it's kind of a definition. And so there exists a, well, again, unique up to additive constants. And that's again an exercise. Repelling, sorry, I'm saying nonsense. This is actually unique, but we don't need it. Repelling Fatou coordinate. After I fix my, again, parametrization. All right, that I'm going to call psi of f from C to C, semi-conjugating the translation by 1 to f, which means that I will have that phi of f of z plus 1 is going to be equal to f of, well, u plus 1, sorry. It's going to be equal to f of psi of f of u. All right? So now, this time, the translation by 1 is inside the variable. and such that I don't have much space in here. Well, I'm going to try to write it. Psi of f of u is going to be equal, so this is a little nastier than before, minus 1 over u plus b log minus u plus little of 1 as the real part of u goes to minus infinity. And yes, I'm not going to give you this exercise because I didn't give you the proof of this. And so now, yes, it's a global map. This one is a global map. And this is why we call it a parametrization. Well, actually now, so I'm going to introduce a map. And for the moment, we don't really understand why this map. So, but actually, instead of doing it like this, let me do it as we got there. So how did we got to this wandering Fatou component thing? Well, we got there by this. So now remember how this Fatou, well, how this skew product that I presented to you yesterday was done. So our original skew product, I'm going to call it, I don't know, well, capital F tilde, because I used capital F today already, so of ZW is going to be Z plus Z squared plus AZ cubed plus pi squared over 4W. And we don't really understand why this pi squared over 2, but for the moment you believe me. And then we have W minus W squared plus whatever. Okay? So now, so this is G, and this is F, and this is the transform. This is F of Z, this is G of W, and that's the perturbation that I put. Okay? So what happens when I iterate it? When I iterate it, k times, well, let me put an n because it's kind of easier for me. ZW, well, this becomes a mess. So this is something that we don't want to write for the moment. But this is what? This is Gn of W. All right? So this behaves like 1 over n. I mean, if I wait n to be long enough, for long enough time, this is 1 over n. So what happens? So let's just take the first iterate of this. Well, let me write down for 1 second what is this with respect to Fn plus 1. Fs plus 1 of Z naught W naught is simply, so let's write it down, Zn plus Zn squared plus AZn cubed. Okay, so this is easy for the moment, plus pi n over 4 Wn. And in here I have Wn minus, well, I have Wn plus 1 in here. Okay? And so, well, if this was not moving, so this behaves like 1 over n plus 1. But in here, it's like as if I had 1 over n. All right? So if this was not changing, so I have a perturbation, and if I was always composing the same map with itself, I would have what people called an autonomous system, which is perturbating. So the idea is, so the idea in here, first we understand the case of F epsilon, well, let me write like that, to some iteration of Z where F epsilon n of Z is of the form Z plus Z squared plus, AZ cubed, but this is not exactly important, plus our epsilon n, and I'm going to put a square because it's easier, so actually I'm going to do two things. I'm going to put it here like this. First, we understand the iteration of this map where I'm just putting an epsilon. I'm just perturbating my map. and I'm iterating once more, and then maybe I will have to have some relation between epsilon n and n to be able to prove something about this. And second, there is a t missing. And second, we remember that, yes, we remember that at each step, this is changing. Okay? So at the n step, and the n plus 1 step, I'm perturbating by 1 over n. But at the next step, it's going to be 1 over n plus 1. And then 1 over n plus 2, and so on and so forth. And so, well, it's going to be a mess, because it's not going to be autonomous anymore. So then we understand, we study the non-autonomous iteration. Okay? And so in here, so let me write down stuff before, and then I will give you a proposition. We will do the proof, and if there is more time, I will tell you a little more on this parabolic implosion, guys, stuff. So this is called, so this brings, well, this is related with what usually people called parabolic implosion. Because in here, if you now compute, now you're an expert. If you now compute the fixed points of this map, since epsilon is non-zero, you're going to get 2 fixed points. Okay, it could be that your 2 fixed points are like this, or it could be that your 2 fixed points are like this, or of course in any possible direction, but the worst cases are either your fixed points are like this, so remember you had a repelling and attracting petal. So this point could split into 2 fixed points. I ask you as an exercise to compute the multipliers at these 2 fixed points, and you will see that in this case, this one is slightly attracting, and this one is slightly repelling. What I mean slight is that epsilon is very small. So this is as multiplier which is less than 1, but really near to 1. And again, this has multiplier which is bigger than 1, but near to 1 as well. Okay? But it could also go, so this is one extremal behavior. It could also go like this. So you have this fixed point, and instead of splitting like this, it splits like that. And now what happens is that these 2 multipliers are both slightly bigger than 1. Is 1 plus an imaginary number. If you are in this case, well, actually, so, okay, have you ever baked a cake in your life? Have you ever used this, I don't know how to name it in English, so have you ever done this whites of the eggs, like snow whites of the eggs, right? So what I hope you don't do it by hand, because it's really hard on your arms. Usually one uses an egg beater. So what's the idea of an egg beater? It turns, okay, which means that the liquid passed in the middle, and that's exactly how it's called. So this is so there was this person in complex dynamics, Adrien Duhady, whom I didn't meet, unfortunately, but it was a very crazy, this is not going to go worldwide, right? It was a great, crazy person, maybe a little like myself, but so he really liked to name things. So, and he saw things. So for example, in holomorphic dynamics in dimension 1, you have all this bunch of things which are called the basilica and the rabbit and the airplane. And he's really right. I mean, if you look at those, it's like, oh, you see a rabbit. You're right. I mean, he's right. And you have little elephants in the motherboard set. And that's right. I mean, you see them. You see the little elephants. Search it online. It's amazing. And in here, what he is one of the fathers of parabolic implosion. And in parabolic implosion, what he says is like, in here, since you are slightly repelling and slightly repelling, if you're both repelled from up to down, well, if you pick a point in here, then you start going through this gate, as the gate we pass every morning. And in here, well, this is slightly repelling, this is slightly repelling. The only thing that you could do, well, you have to go forward. And so in here, you had this sort of gate which was closed, where every point was going to get smashed. I mean, the idea is that you're trying to tend to the origin, you never reach the origin, but you're converging to the origin. But in here, there is no, I mean, the origin doesn't play a role anymore. And so you pass through the gate. And so this is called the egg beater. Like if you were doing a cake in dynamics. And so now, in here, yes, okay, yes. So let me, okay, all right. So let me define things, and so that at least I can give you the final proof. Maybe I will not talk much about Lavor's maps, and how we get there, and how the study goes, but at least you will get the results, and you can, I hope that in my notes, they are written well enough that you can understand them. All right, so definition, the Lavor's map well, there is a phase of phase 0, but you don't care about it, just to be precise, is the map which we call capital L of F from the basin, the parabolic basin to C, defined as, well, it's simply the composition of, well, I'm taking the attracting Fatou coordinate, and I'm pre-composing it with the repelling Fatou parametrization. Okay? So that's a map. So this is, it's simply what we're doing. I mean, of course, where can you do this? Well, and this is why we need to use the fact that we are taking the inverse of the repelling Fatou coordinate. So in the Fatou coordinates, well, you remember you had these intersections, and you had, if you consider the attracting Fatou coordinate and the repelling Fatou coordinates, they are both defined on these guys, and you can compose them there, like as if they were changes of coordinates. But this doesn't give you anything in a neighborhood of something, right? It's just, and it's, and there might be a difference in between what happens on top and what happens on the bottom. And this has been studied. These are called horn maps. So in here, what we are using is essentially the inverse. Well, it's related to a horn map, but it's not exactly the same. So this map is going to be defined on the full basin of the origin, which is kind of a lot. And now, yep. So now Lavor's result is the following. So there is a theorem by Lavor's in 1989. And what he says is that let f of z be of the form z plus z squared plus, z squared plus big O of z cubed be a polynomial. And so let Mn be a sequence of integers. So these are going to tell us the iteration times tending to infinity. Okay, and let epsilon n be a sequence of complex numbers tending to 0 as n tends to infinity. Such that, so now I'm going to tell you what I need. Mn minus pi over epsilon n tends to 0 as n goes to infinity. So essentially what we are saying is that epsilon n is essentially pi over mn. Okay, if you write it in the other way around, this is what this is saying. Then yes, so i.e. epsilon MBA is like pi over mn. Then what happens is that the map f plus epsilon n squared iterated mn times converges as n goes to infinity to the Lavor's map of phase 0 uniformly on the basin B of f. Okay? So this is kind of very powerful because in order to see what happens if I do this composition of this iteration of f, I only need to know something about my original f naught. And so, well, the key proposition, I have 5 minutes. I remember those. Okay, the key proposition that we proved, so this is the key point and this is the technical part. So the key proposition is that, yeah, there are 2 key propositions, but, well, a first key proposition, this is one-dimensional, is that if f of z is of the form z plus z squared plus az cubed plus O of z4, and A is sufficiently close to 1, so 1 minus rho for rho positive, for rho small enough, then the Lavor's map has an attracting fixed point. On B of f. So the Lavor's map is going to have a point in the parabolic basin for which it is going to have an attracting fixed point. Okay? And so the key proposition that we need, so the second, well, the really key, like a capital key proposition, is that as n goes to infinity, what we have is that the sequence of map where we take ZW and we send it to, so I'm going to iterate f tilde, and I'm going to iterate 2n plus 1 times at the point z, g iterated n squared times of w. This sequence converges uniformly on the basin times the basin of G to the map ZW coming from, sorry, this product. And where does it go? Well, this guy, when you iterate it with capital F 2n plus 1 times, I'm simply iterating G n squared plus 2n plus 1. And I'm sure you all know that this is equal to G iterated n plus 1 all together square times. Okay? And so when you send T n to infinity, this is going to convert to 0 because we were in the attracting basin of the origin for Z. So in here we have a 0. And well, now there is no surprise if I tell you that it's going to go towards the Lavor's map. So in here, I'm going to have the Lavor's map of f at z, which is one-dimensional, and at 0. And so this belongs to, again, the parabolic basin times, well, actually, we can be even more precise, times 0. Well, sorry, c. Let's put c in here. All right, so I know that I only have 1 minute now. So why is this working? Because, yes, so with these two propositions, now what we have, so I'm not going to write the formula, I'm just going to tell you how it goes, how the proof goes, because I have 1 minute. So now I'm going to, so what do I have? I have, if I take A close enough to 1, less than 1, for example, I have this L of f which has an attracting fixed point. All right? And so I will have, and this sequence of maps is converging there. All right? So I'm going to consider a little small tiny disk around this fixed point. So I have this W here and this vertical Z that I write like this. So in here I have my parabolic basin, so this is B of f. And say I have a psi in here, which is attracting, but not for f, for the Lavor's map. I'm taking a tiny disk in here, and I'm taking a preimage of a tiny disk somewhere. So now you're going to hate me. I know, because I hate myself as well in here. So now I have this. So this is the horizontal one. This is in the z plane. Okay? So in here I have something. I can take whatever disk I want. I will converge to the origin. And now I'm going to take a product of these guys. And I'm going to see what happens when I iterate f n square times. Well, when I iterate f n square times, I'm going to converge to what? Well, in here I'm going to converge to 0. And in here, I should converge to the Lavor's map. But you know, well, I'm going to converge to this fixed point. And so what we have is that you can find, so you find this product of disks. Well, there are some preimages to take, okay? So on this, we can prove that f iterated n squared times is converging somewhere to actually psi 0. Aha. But this is an open set. It's a product of two open sets, which are actually even simply connected. So we have some open sets where we converge somewhere. This open set that I'm going to call, let's say, W. So W has to lie inside a Fatou component omega for f tilde. Okay, so now we found a Fatou component. How do we prove that? So this is a Fatou component, and by analytic continuation, so now we're going to use analysis. By analytic continuation, on this Fatou component, f n squared always converges to xi 0. Now let's see what happens to its images. So if there exists k different from h such that one iterate, so the kth iterate of omega, is equal to the h iterate of f on omega. So if there is a moment where it goes back to itself, to one of its images, then fn squared restricted to this, well, let's call this omega k, and let's call this omega h. If I restrict it to omega k, it's going to converge to little f iterated k times of psi 0. And when I restrict it to omega h, it's going to converge to little f iterated kh time sorry, H time oxide, omega 0. But now, and I'm done. I know I'm overgoing, but I need to do it. I mean, at least the final. So now, this means that if these two are equals, again, we are going to use analysis 1 from the first year of undergrad. Since we have uniqueness of limits, f omega h is equal to omega k, then fh of psi is equal to fk of psi. And this is a contradiction because k is different from h, and psi lives in the parabolic basin of f. And in the parabolic basin of f, the only periodic or pre-periodic point lies on the boundary, and it's the origin. And this is how we proved, well, more or less, I didn't give you all the details, how we proved that we could find a wandering domain in dimension 2. There are so many things that I didn't tell you, like there are many results. So this gives you a family of Fatou components, which has an infinite orbit. And now there is a new result by Mathieu Astorg and Luca Bochtaler, where they prove that not only you can have this, but you can have infinitely many different, such orbits, such infinite orbits. So you have infinitely many different wandering Fatou components. And there are so many things that I didn't tell you, but my time is over. Rafael is looking at me since 5 minutes now. It's like, nah, come on. So I'm going to stop you, and thank you very much.